Welcome back, students, to Chemistry Unit 3. Today we'll be talking about Unit 3.3, Periodic Trends. Yes, we are going slightly out of order. 3.2 we will actually do after this because 3.3, Periodic Trends, includes first ionization energy, which we talk about in 3.1. So I think this unit lends itself well to what we just talked about. So there are 4 periodic trends you have to know. We've already talked about first ionization energy, where as you go across a period, the first ionization energy increases, and as you go down a family, first ionization energy decreases, meaning the highest first ionization energy would be all the way over to the right and near the top. So helium has the highest first ionization energy. There are 4 periodic trends you need to know. Really, it's 3 trends and 1 concept that you have to know in order to make it through this course. All periodic trends are a pattern that arises on the periodic table. As you move across a period and down a family, a pattern emerges. And those patterns affect all sorts of things in chemistry, from types of bonds to strength of intramolecular forces. Periodic trends play a huge role in this course. To explain any periodic trend, the easiest way to explain it is what we've learned so far, that as you move across a period from right to left, there's an increase in the nuclear charge. So in that second period, when you go from lithium to fluorine, there's an increase in the charge within the nucleus from 3 to 9. That increased nuclear charge will increase the attraction of electrons for that nucleus as that nucleus becomes more and more positively charged. Periodic trends can also be explained from top to bottom. As you go down a family, the number of shells around a nucleus begins to grow. From hydrogen with a single shell around the nucleus to francium with 7 shells around the nucleus. Those shells push electrons further and further away, weakening that attraction. Because the closer 2 objects are, the stronger the attraction between them. We've already discussed first ionization energy, that the amount of energy it takes to remove an electron can be related to the force of attraction for that electron. That force of attraction is proportional to the charges, so the nuclear charge versus the charge of an electron, divided by the distance between them. So as your nuclear charge increases, it becomes increasingly difficult to remove an electron. So as we move across a period, first ionization energy increases. As you move down a family, there are more and more shells around the nucleus, pushing those electrons further and further away, weakening their attraction, so it becomes easier to remove an electron. Periodic trends are a trend. They are things that tend to happen. They are not an explanation. If on a free response I ask you to explain a periodic trend, simply saying something is below another, or saying that, hydrogen comes before helium on the periodic table, is not an explanation. An explanation needs to include one of the 2 explanations we've talked about. That first ionization energy decreases from top to bottom because there are more shells, or a higher principal energy level, if you want to use the technical term. And as you go across a period from left to right, there's an increase in the nuclear charge, the number of protons in the nucleus. These are explanations for a pattern that you would need to put on a free response for your test or quiz. So a new periodic trend, one we haven't talked about yet, is atomic radius, the size of an atom. From the nucleus to where there's a 95% chance to find an electron. Now that percent chance of finding an electron never actually reaches 0. There are some theories that the last electron of an atom is on the other side of the universe. However, in this course, we'll simply use that 95% to define the edge of an atom. So as we look at atoms, so the size of atoms, their radius, is related to that attraction. If I have two atoms, which one of these would be smaller? Well, the one with the greater attraction would be smaller. That larger attraction will actually pull the electron closer towards it. So as nuclear charge increases, atoms get smaller. Up to a certain point. At some point, you start growing shells. And as you get more and more shells, that pushes electrons further away. So the size of atoms actually decreases as you move across, as the nuclear charge increases. As nuclear charge increases, it pulls those electrons closer and closer to the nucleus. So the smallest atoms would be furthest to the right. Atoms get larger as you move down a family, as the principal energy level, or the number of shells, increases. The more shells you have, the further it pushes those electrons out. So the largest atoms would be furthest down and furthest to the left. Related to size is how that nucleus attracts electrons outside of the atom. This is known as electronegativity. If there is an electron outside the atom, how much does that atom pull the electron towards it? And you can relate it to size. The greater the nuclear charge, the smaller the atom is. Since it's small, the electron on the outside experiences a stronger attraction for that nucleus, since it can get closer towards it. But when an atom is very large, the electron on the outside experiences a weaker attraction, as it can't get as close to it. So small atoms like fluorine have the highest electronegativity. They attract electrons the most. Large atoms like francium and cesium have very low electronegativities, as they are the largest. They attract electrons to them the least. Electronegativity is determined based on bonds. So we actually don't have any electronegativity values for noble gases, because noble gases don't form bonds. Now, I'll grant you, xenon actually does, and I'm sure that this video is slightly out of date. You could find an electronegativity value for xenon, but I don't know what it is. So it's not relevant to this course. Long story short, electronegativity values are a scale from 0 to 4, with 4 being the highest. Fluorine has the highest electronegativity values, and 0 being the noble gases, and it decreases as you move away geographically from fluorine. No one will ever ask you the actual electronegativity values, except for maybe fluorine, because it's always the highest. It is always 4. However, you are expected to be able to predict which of these are most electronegative, which atoms are most electronegative. So oftentimes the AP exam or the SOL will give you four elements adjacent to one another and ask you to say which is the most electronegative, which is the least electronegative. So remembering that electronegativity increases as you go across the period because the nuclear charge increases, thus pulling the atom closer together, and knowing that as you go down a family, electronegativity decreases because of increased number of shells pushing that electron cloud further from the nucleus. Our last periodic trend that you have to know for this course is ionic radius. An ion is a charged atom of an element. Some elements will gain electrons and some will lose electrons to be like the noble gases. The noble gases have the least amount of energy of all atoms of all elements on the periodic table, and everything in the universe strives to be at the lowest energy configuration possible. If I gave you the option to finger paint or learn chemistry today, you would all be like, I am making a turkey and I'm going to use blue and red, because that is an easier task. That is the lowest energy configuration for you. Atoms are the same way. They will alter themselves to be like a noble gas, to have the same number of electrons as a noble gas. Metals have more electrons than a noble gas. So, for example, potassium has 19 electrons. If it had 18 electrons, it would have the same number of electrons as a noble gas. It would be at a lower energy state. So potassium will lose 1 electron, giving it 18 electrons. It still has its 19 protons, so potassium develops a +1 charge, forming a potassium cation. In fact, all of the alkaline metals are all 1 more electron than their noble gas cousins. So they will all lose 1 electron. They all form +1 cations. Alkaline earth metals are 2 electrons more than a noble gas. So barium, with 56 electrons, will lose 2 electrons to be like xenon. It still has 56 protons, so all alkaline earth metals develop a +2 charge. Transition metals develop all sorts of odd charges, and we'll talk about them later. There are some you do need to know though. Silver, zinc, and aluminum always have the same charge. It always goes +1, +2, and +3. You're responsible for knowing that aluminum is always +3, zinc is always +2, and silver is always +1 when forming a compound. When you lose electrons, your nuclear charge stays the same. So with less electrons to attract towards it, that attraction grows. Less electrons mean less repulsion, so cations, positive ions, you can remember cations are positive because the T in cat looks like a plus sign. Or you can remember that cats are positive. Cations always shrink in radius. So when you form a cation, the radius of the atom decreases. This is why neutral atoms that form cations show massive decreases in their radius. And the more electrons you lose, the greater that decrease in your radius. Nonmetals have too few electrons or less electrons than noble gases. So nonmetals form negative ions called anions. So you can remember that cations are positive, anions looks like the word onions and they always make me cry. So that's how I know they're negative. It's not a perfect system, I know, but it's all I got, man. Anions are negative and traditionally are non-metals. So the halogen family are always 1 electron short of a noble gas. So all halogens actually gain an electron. They still have the same number of protons. So bromine, when it becomes bromide, goes from having 35 electrons to 36. It has 1 more electron. It becomes a -1. Now you'll notice I no longer called it bromine. It becomes bromide. That's because nonmetals and their anion counterparts are very different chemically. Fluorine gas is a gas that's a brownish cloud and so reactive that anything it touches instantly lights on fire. It has a massive amount of energy because it is that 1 electron away from being a noble gas. However, when it gets that 1 more electron, when it has 10 electrons, a -1 charge, it no longer is a brownish cloud. It actually forms a salt called fluoride. it chills out. It doesn't light everything on fire. Fluoride is what is in your toothpaste. We go from something that ignites everything it touches to something that you can use to kill off bacteria. Anions have drastically different properties than their neutral counterparts, so we change their names. Any anion gets its ending changed to "ide." So things like fluoride or chloride or oxide. These would be anions of neutral atoms. The chalcogen family are 2 electrons short of a noble gas, so they will pick up 2 more electrons. All of the chalcogens will form a -2 ion. Nitrogen and phosphorus are the only 2 non-metals in column 15, so they will form a -3 charge. Or oxidation state is a fancy word for charge. As you have more electrons, those electrons repel each other more. So anions actually grow relative to their neutral counterparts. Fluorine shows a pretty sizable jump, almost doubles in radius when it becomes fluoride. The more electrons you gain, the larger that repulsion, the bigger the jump. So a -3 anion would be way bigger than a -1 anion. And with that, you are able to do page 23 in your packet. If you were in class, I might have given you an additional worksheet that I prefer to this. However, if you're not in class, you can do page 23 for practice. You also can do the note quiz questions that go with 3.3, with the exception of number 1. The answer to number 1 is J. So record J for number 1, but then you will be able to do 2 through 10. I'll see you next time when we talk about electron configuration and magnetism.